Okay. So the hydraulic data, as I mentioned, commonly we might only focus on the groundwater systems. So like the water conservation concept using a box to do this kind of work. But for overall, you should understand more completely from the climate conditions from the outside atmospheres, and then to the surface water systems, and then you will able to connect to your groundwater system, and that will be more complete. And so this is the kind of the input to your systems. And another could be you need to understand like outside, inside and outside part. So this one could be a kind of recharge concept, and they'll be able to provide you the information. And another could be the discharge. And discharge, that could be separate to two kinds of the conditions. One of that is the natural discharge, like we mentioned, the submarine groundwater discharge. They naturally outflow to the seawater systems or to the sea systems. And another could be the pumping activities. When you have the human activities, you might have the pumpings. So you induce like the whole box systems, you have the pumpings. So you might not able to have the sufficient water for that issues. So recharge and discharge is the very important component for the groundwater system. And recharge, another part is one of the main part will be from the rainfall recharge conditions. Another could be from the surface recharge, and furthermore, it will be from the mountains. Okay, so the next lecture we're talking about from the mountains to the plant for the groundwater system. So how the mountains waters flow to the plant area to have the recharge your groundwater system is a very important issue together. So commonly from the we call the boundary concept, there could be the recharge and discharge outside. And for the inner part, we might have the another recharge. Sometimes we use in the like a manager aquifer recharge concept, artificial recharge conditions. Another could be the discharge pumpings. And furthermore, if we would like to assess the property for the groundwater system, we also need to conduct a pumping test. For pumping test, it will be more able to provide the in situ quantity for the free flow. So the transmissivity and storativity will be the two components we mentioned in the previous talk. We use in the pumping test to estimate the transmissivity and storativities. So in the future lecture, we're talking about how to use in the pumping test to estimate the transmissivity and storativities, and then how to analyze. We provide you the data, and then how to use in the data to estimate the T value and S values based on TICE solution for that. And hydrochemical data can be separated to three components. The major ions is able to use in understand for the condition for the water. Like one of them is water source. They are based on the rainfall recharge, or they're based on the period groundwater system, or they from what kind of the component, like they connect to the river or connect to the pond. If we measure the major ions, we are able to do the comparisons between different kinds of water bodies. We are able to not only understand the contribution, we can also estimate the compositions. How much percentages come from which kind of water bodies, and then we are able to combine them together. And some of the major ions can also be used to trace the water source. For example, in the geothermal systems, we take the water samples to do the analysis, and then we will be able to use in the chemical compositions to understand if they are come from the rainfall system or they are from the much deeper, the deeper part. I forgot exactly how the term. Okay, from the magma system or even deeper systems. Their composition will be different. So they can use the composition to quantify or to estimate where could be the water source to this system. And that will be a very important part, because if they are from the rainfall systems, and that means they are easy to be replaced, and they'll become more sustainable use. But if they are from the paleo waters, that means they might not have sufficient water source. And after you use that, they might be dry, and they will not able to sustainably use. So that will be a very important part to understand the source, okay, using the major ions. And salinity is the issues for the seawater intrusion. In the coast area, if you have the salinity higher in the groundwater system, that means they might have the intrusions from the seawaters. But this kind of problem, they could be from two ways. One is they come from the aquifer system into to your freshwater system. Another could be like floodings, the seawaters flooding to your land and then become infiltration to the groundwater system. So they have two ways to contaminate your groundwaters. And both of them will induce the salinity increase. And furthermore, you might have another source, could be like contaminations. Rivers, if the river have the high salinities, they might also affect your groundwater system. Or even some of the industrial waste waters. Some of them will have the high salinity also affect the system, okay? But many salinities from the seawaters. And the third part will be the contaminant and also the traces. Contaminants, the many contaminations, pollutions, we easier to understand that. And traces could be the nature or the human induced. Like for the natural traces could be like an isotope. Isotope, H and O, they have the isotope. They will be able to trace the source or to calculate the compositions and understand like the water is from which elevations. They could be from the top mountains or to the plain area. Their percentage, HO percentage will be different, isotope. Now, so that's the hydrochemical or the geochemical compositions for the traces. And another could be like a chloride. In some of the experiments, we try to put some of the traces. Traces means we will be able to identify their path, okay? So we put the traces in the wells and they might spreading. So we might be able to observe in the downstream area. And then we will able to know one of that is the speed, how fast they're traveling to another wells. And another is how they move this direction or these directions. What's the direction they move? You'll be able to trace their direction and also the flow rate like that. But this tracer test is, you need to be careful because as we mentioned that the particle movement, water flow is very slowly. So if the particle movement is very, very slow and you want to assess like a 100 or several hundreds meters away, you might not able to get the result. For example, it traveling from this point to 100 meters away, it might take 1 year. And that means you need to wait in 1 year to detect the tracer. It might be time consuming. And if your project is just 1 year, you cannot use in this kind of tracer test, okay? You have high risk. Another is that you expect they have 1 year to travel on to there, but maybe you're waiting 2 years, 3 years, 4 years, no tracer observed because it passed through to another directions. It passed through to the deepest, okay? And your wells is not able to detect that. So they become very high risk. Tracer test is very depends on the flow path. Okay, so the flow path is very important. You need to confirm the flow path, and then you will be able to use the tracer test. And for the sediment, it's really easier because sediment is more homogeneous. But if you using a tracer in the rock systems, they'll be very, very dangerous because the fractures is uncontrollable. Okay, you don't know which fracture connect together. So you put the tracer here, even 10 meters away, you cannot find anything. Okay, even though you know that the flow path is from this way to that way, you have the wells here, maybe several wells, but you put the tracers just 10 meters away. You put the tracers, you cannot find anything. Disappear, okay. It might penetrate to the very deeper or to the other place, you don't know. But because the fracture system connection is very complex, it's not easy to use in the tracer test. But if you're using another, like the pressure, if you're using the pressure, like you pulse the pressures in one wells and try to observe the other wells, you might be able to see the response. Because pressures, they can propagate to any connected pore spaces. if your pore spaces or your fracture have connections, they have the response. But the tracer only move from downstream to the upstream to the downstream. Okay, they only have the one pass flow, and even if you have the preferential flow pass, they mainly flow to that area, and the other press do not have that. So tracer test is very limited. It's not easy to observe the connections. But if you use in the pressures, like you can also use in pumping, you pump, you can see the others have the response, and you will know how larger connections between two wells. Okay. So pressure will be easy to have the observation, but tracer is very difficult. And recently, like Professor Ni's lab using the thermals, there could be another. And thermal have another problem is that thermal not only move with the waters, it also move in the solid phases. So when you see the thermal, you see the temperature changes, they could be affected by the waters. They can also affected by your solid. Okay. We know the tracer, like if you put the chlorides inside, they only move in the pore spaces. So they need to follow in the channels, flow channels. But if you put the temperatures inside, it can flow with the water flow channel, water channels. They can also have the diffusions with the solid phases. Okay, so sometimes they will become complex. And another could be your temperature will be like a kind of attenuate, because they were spreading out. The temperature will be easy to be diminished. They'll disappear. Okay, so you cannot have the long distance. Your distance is too long. Your temperature can also not easy to be observed. Okay, so temperature have another weak point for a kind of tracers. So yeah, so be careful for these kind of issues. Although we know the contaminations or contaminants could be important issues for the hydrochemical, and another is the tracers. And like some professor in the geothermal system, they proposed that we should use the tracer to identify the flow path. But honestly speaking, it's not able to work in there. If they ever doing this kind of test, they will know that's almost impossible. Rock system is one of that. Another is the distance. As I mentioned, you put like we have the geothermal system. We have the pumping well. We have injection well, right? Commonly, we use like a kind of cycle to maintain the geothermal system. So we use the pumping wells and injection wells, and the well's distance is several hundred meters. And our expectation is that we pump the hot waters and then inject the cool waters. And we don't want the cool water moving too fast to our production wells, because they become like the cooling front. You will let your temperatures decrease, and you do not able to run your geothermal system. So we hope the water is moving slowly, and then they can be heat up again, and then going to here, and we will be able to become a loop. Okay. So that means that the propagation from the injections to the productions, commonly it takes several years for the propagations, several years. So if you like to using tracers, that means you put the tracers inside. It might take several years to reach your pumping wells. And after you got the data, you already run several years, and then how this data be used. Okay. Because they want to know if this kind of loop is workable, or if the time is sufficient for the water to move in like a kind of loop. But after you got the result, you already spent maybe 5 years. And commonly 20 years is for the geothermal system to operate for a life. So you only spend 1/4 of the years, 1/4 of the time to do the test. This is just the test, okay? So it's not an economy makes sense. It do not make sense for these systems. You cannot use in the tracer to do this kind of work, but you can use in the pressures, like you pump, you inject, you will be able to see the response immediately, because Zixin will know that the pressure propagation is much faster than the fluid movement. we use in particle inject, and then we can put another, so they become a loop. But that is pushed. The water is pushed one by one, not the particle moving from this point to this point. Tracer is the particle need to put inside and then move into here. You can observe. So it takes much more time. And pressures don't need, and even the water system don't need. Okay, you can easily see the push waters be observed here. So the pressure will be easy to do this kind of test, but another tracer. So I tell that professor, that a very senior professor, is not workable, but he do not agree. I don't know. Okay, and following will be, we know we have the geological data, we have the hydrological data before we do the hydrogeological survey. We can try to get some of the data we already have. And some of that we can also do in situ. Okay, so we do the hydrogeological survey for this kind of data. So in the following lecture, we were talking about how to do this kind of survey, but maybe not complete. We will introduce several methods to do hydrogeological survey. The main work will be if we have the data and then how to use the data to construct the system or construct the hydrogeological models for your research assessment or to support your research. The most important part will be this part, not the really go to the field to do the investigations. Okay, so my part will be focusing on this way. And after we doing the surveys, another way is that we need to collect the soft data. The previous part will be mainly for the solid, although not exactly solid, but for like a more geology or for some of the in situ, for the intrinsic properties, in situ properties. And then another could be we need to have some continuously observations, not only the physics, also the chemical part. Okay, so we need to have the spatial temporal observation. Although AI provide me only very few, he only provide 1, 2, 3. This 3 point, and another is the quanta level, but I think it's not sufficient, so I modify the content. So observation data, and I put further is analysis. So we need to collect the spatial temporal observation. Commonly, when you have the project or the work, you go to the field, you need to make the decision how many maybe points. Okay, the first would be the point to do the survey. And the survey could be solid and also the soft. Soft could be you drilling the borehole layers, and then after that you put the device inside to do the management. Okay, to do the measurement, not the management, to do the measurements for the water levels. And sometimes you might go there to take the water sample back to do the chemical ion analysis. Okay, so that will be two-way. But the chemical analysis commonly is not easy to have continuous measurements. You might take sample like every month, every week, or every season, have one sample back to do the analysis. Although some of the device right now is able to have continuous measurements in situ, but it's not very popular. Commonly, we continuous measurement will be the water level or parametric CAD. So we put device in situ to do the measurements for the water levels, and we will be able to obtain the overall water level from net. And after you have the observations, water level is one of the points. Another could be your chemical compositions. They might have the seasonal variation, or they might have the long-term trend. Like for the groundwater management issues, we commonly need to see if the trend, the water level trend is declining or uplift. They have the seasonal variation. I think there's no problem. Commonly we have that. But after the seasonal variation, you might able to see the trend is the decline or is uplift. For example, if you would like to assess the water resources, the continuous decline might induce the depression problems. You might not able to have the sustainable management. So you need to control your pumpings. Or the hot spring area, your groundwater level continues to decline. You need to be careful for that issues. So time series analysis is very important. Okay, so we commonly see these two, long-term trend and seasonal variations. Long-term trend to that you understand the background, if they uplift or decline. And signal variation will be able to see if how large this variation might have. As I mentioned, they could be connected to the water resources or the engineering work or the hazards issues. And if we see the larger variations, sometimes you will able to control, like a pump, you can pump in the wet season, but you need to prevent pumping in the dry seasons because they might too lower and your pumping might have to compete. Like if the pumping is for the public water resources, like Taiwan water corporations, they pump the water for the public use, but you also have the local people, they pump the water for the drinking or for irrigations. You might have the compete problems. And if the water level too lower, their pump will be spoiled and they might broken. Okay, because your pump need to put in the waters. But if your water level decline here, they will continue to pump, but they will become very hot and then broken. So you cannot let the water level too lower and to prevent the compete problems. So the signal variation is also quite important for some of the management issues. And like in subsidence issues, you also need to take a look at the signal variation. Subsidence commonly occurred in the dry season or in the decline patterns. When your water level declined, you have the drainage behaviors, and then your soil will be compressed. Okay, the same total stress equal to the effective stress and water pressure. Your water pressure decline. That means your effective stress need to increase. And your effective stress increase, they'll be compressed. Okay. And some of the soil, if you over the, we call the over consolidation conditions, they will become the permanent deformation. So you need to be careful that you are not able to let the water lower than the historical levels, and they will induce some permanent deformations. If they are within that, they will become more elastic behaviors. You will not have the permanent deformation. They become elastic. Dry season and wet season, they become elastic. They can recover, and they will not induce the problem. Yeah, so seasonal variation is also a very important part. And finally, I also state some others, like climate and hydrology correlations. Some of the interesting issues that groundwater affected by the climate and also the hydraulic. For the climate issues, the barometric pressures affect groundwater system. Barometric pressures, commonly they might affect the groundwater system, could reach several centimeters, although not large. Depends on what target you would like to assess. What you assess, the quantity is relatively small, so they will become larger affected. But if your quantity, like you assess the groundwater resources, and then several centimeters or 10 centimeters might not be significant to affect your result. So barometric effect could be ignored. Okay, but if you assess some others, you should be careful. Like when typhoon coming, there's the low barometric conditions, pressure conditions. Your groundwater level will uplift largely. That could be over 10 centimeters. Okay, so that might affect some of the behaviors. Okay, but not very seriously. And like if you have the tidal, if your wells is close to the sea in the coastal area, your tidal variations also affect your groundwater system. Okay, so you're able to have some of the variations to influences. Yeah, so that could be interesting part. Another could be the rainfall, how the rainfall influences to your groundwater system. As I mentioned, in Taiwan area, commonly the recharge is relative depth, so the groundwater level is quite stable. But in the alluvial plain area, like in the Zhousui River alluvial fan and also the Pingtung Plain, we can see the variation is quite large. And also in the eastern Taiwan, there's the gravel materials. The variation could be very large. Okay, so this quite depend on the hydrological conditions. And they imply the ability for the local informations. And human activities can also affect, like if you have the agriculture nearby your observation systems, then your pumpings affect largely for your observations. And you are not able to assess more nature's background. For example, we commonly put observations, groundwater observations, to understand the nature variations for your system. But if you have the nearby pumpings, it largely affects your observation, that your observation becomes useless for the natural conditions. But it can reflect the activity for the human. That could be okay. So it depends on your purpose. If you would like to assess the natural variations, and then you need to avoid the human activities. And another issue is the other triggering, like earthquake. Earthquake affect largely when you see the groundwater level have the very abnormal increase or decrease patterns or the signals. You can first check if you have any earthquake events around that period of time. And commonly, if you this kind of step changes, you commonly can see that's the earthquake-induced triggering. And big earthquake will have the very strong influences. Like for the Shih-Jung earthquake, it increased the water level more than 1 meters. Okay, and in the eastern Taiwan, they could be much larger. And that depends also on the hydrogeological conditions. Now, maybe in the later lectures, I can try to put some of the observation we observed. There's a Yuhao do the assessment. We see a lot of the level decline or uplift. And the decline behavior could be more than 10 meters. Okay, it depends on the hydrogeological condition. Like in the eastern Taiwan, the hydrogeology is mainly for the gravels, very coarse materials. And another could be they are the tableland. So the elevation is relatively higher than the mean sea levels. So after you have the earthquake shakings, you might easy to have the damage for your sediment system. And your sediment system be damaged, and then you will have the very large decline of the water levels. Okay. So in that area, in the foothill area or the tableland area, you can see the decline of the head. But they will induce another problems. In the bottoms or in the foot areas, you will induce the high water pressures outflow. So that area will have the spring. We can imagine the spring. Another could be liquefaction. So in the Shih-Jung earthquake events, we can see that in the Zhanghua foothill, the foot of the Zhanghua foothill, we have liquefaction occurred. Okay, and that area is we guess is mainly due to this kind of behaviors, because the foothill area is relatively high, and we can see a lot of groundwater level decline. And the decline means that they need to have the water outflow, so they flow to the foot of the foothill areas, and they become like a kind of upward flow patterns and induce the liquefactions around that area. And this phenomenon is also observed in the eastern Taiwan. For the Shih-Jung and Shih-Jung, or I forgot, not Shih-Jung. There will be earthquake September 17 and 18 that time. We have the earthquake events happen there, and we also found that in the foothill areas, the foot of the foothill areas, we also see the liquefaction largely concentrated. They're very similar. We can see the decline from the foothill area, and then at the bottoms, we can see the liquefactions occurred. So this kind of behavior is very obviously. So it might induce some others, like a liquefaction, or also another is a decline of the water levels. Another information to let you know that if I do not open a course for earthquake hydrology for a long time, there will be a case during maybe the Sumatra earthquake events. There will be wells away maybe thousands of kilometers away from the Sumatra earthquake epicenters in China. The wells become eruptions. The eruptions height could be around hundreds of meters. Originally, they do not have any like a foreign artisan wells, but after the earthquake happens, the wave propagation or the energy or the stress influences that the wells become foreign artisan well and erupt, reach around hundreds of meters. Okay, so you can imagine the influence is very strong. So they also imply that earthquake happens may also induce very strong increase of water levels. although they quite depend on the conditions. And one time, so we go to Japan to take a look at one of the sites. They mentioned that Tohoku earthquake, after Tohoku earthquake, one of the place, originally they do not have the spring, hot spring. They do not have hot spring, but after Tohoku earthquake, the hot spring become naturally outflowed and very strongly. And that time when we visit could be, I forgot exactly the time, maybe around it could be after I come in here, so it could be 2018 or 2018 or 2019, that time. And Tohoku earthquake is 2011, right? If I do not memorize it wrong. So that means that after 8 years, the hot spring continues outflow, strong outflow. And I can directly take a look, there's strong outflow. But they do not use the hot spring because that time they imagine that the hot spring might dry very quickly because they just take place there. So they do not imagine they will have continuous hot spring continuously in that area. So they do not construct any preventions or construct any hot spring pool for the usage. They just let the hot spring go into the canals and drainage out. Okay. But when we go there, still have very strong hot spring outflow. Okay. So you can imagine there's long-term, 8 years, and the flow rate is very strong, continuously. So earthquake will largely affect your hydraulic system, groundwater system. Even so long time, they still continues affected. Okay. Yeah, so be careful for this issue. Although there's another issue, another dirty connect to the this part. And discussion, I think we don't need to talking about. This is AI provided, so I do not directly use that. And after that, AI prepared the slides and suggests me to share some of the case study for the hydrogeological survey here. And he proposed 3 points. One is the Joshua River fan, and for the groundwater extraction and then subsidence. Another is Taiwan coastal aquifers, the seawater intrusion and groundwater discharge. And the third will be groundwater monitoring and also the management under the climate variabilities. So I'm thinking that because I'm commonly asked him the questions for subsidence and the SGD, submarine groundwater discharge. So he suggests these 2 issues in the application part. In the future, I will try to introduce or try to use in our previous research to demonstrate the importances of the hydrogeology for the land subsidence assessments. So that will be the first topic. That next, maybe several weeks after, I will introduce this part. And following, I will also introduce the coastal aquifer, the submarine groundwater discharge, and seawater intrusion issues. That's affected. We can see clearly affected by the hydrogeological materials. It's also done by my lab. So we can use in our previous research to demonstrate that how the hydrogeology influences subsidence and seawater intrusion or other issues. That's quite interesting. And for the management part, I think maybe we do not have time talking about that. So management may be ignored. There will be more approach to the soft part, the water part. So I think we do not talking about too much about that. And the previous 2 will be affected by hydrogeology. So I will talking about these first two issues in the future several weeks. And following, I would like to use in a case study for the hydrogeological survey for installing observation wells in the mountainous area of Taiwan. And this project is operated by the Sinotech engineering consulting companies. Okay, the 中心社. They conduct the complete the survey for the whole Taiwan area. Span 12 years. That's proposed by that time the Central Geological Surveys. They proposed a 12 years project. They spend time for the mountains area to do the groundwater investigations. So from the central Taiwan to the southern Taiwan to the northern Taiwan. So each segments, they spend 4 years for different kind of locations. So the total is 12 years. They try to assess the mountainous areas for the groundwater hydrology investigation. And right now, they try to move to the next phases. Next phases will be the foothill area. As I remember, they might spend 5 years. They want to do the investigation for the foothill area. This part is mainly for the central range, close to the central range. And then the second phase is moving to the foothill area. Okay. Because the plain area is mainly investigated by the Water Resource Agency. So they separate. Mountains is managed by the Central Geological Survey, and plain is for the Water Resource Agency. So this is one of the projects they proposed, and I try to collect the information from their report to share how they're doing this work. So the purpose is to put an observation well, because this project's main target is to understand how much water is in the mountainous area of Taiwan. So they try to put observation wells to do the investigations. There could be several steps. One of that, they're using geophysical survey. They also using some geophysical survey in the whole areas. And the second is they try to use the chemical analysis. And the third will be the solid part. They also do the drilling, geological drilling borehole. They take a lot of drilling borehole. Right now, you will be able to find out the borehole data from hydrogeological database of the GSMMA. Right now, the new name for the CGS. So right now called GSMMA. So you're able to find out the core sample from their website. And so they're using the geological survey for that. And after they take the geological borehole survey, they put the wells in their borehole and then put the parameters inside to do the observation. So originally they have much more wells. They're drilling much more borehole, but at least some of the borehole broken. Some of the borehole is not able to be used. Maybe they are dry. After the drilling, the time they have the water, but maybe several years or several period after they become dry. So they give up some of the borehole. So right now they still have the operation for maybe several dozen of the wells still under observations. Okay. So there's observation wells. They try to put observation well for that. The company, they have separate two different depths, 2 depths for one hole. And observation well is a hole used to observe the water surface at atmosphere pressures within soil or rock. And wells drill into aquifers for the purpose of the obtain water levels, water temperatures, or water quality data. Okay, this is to observe the groundwater observations, groundwater levels, and the other could be they also assess the temperatures and also the qualities, because the original concept is still the water resources. Okay, they want to take the water for the usage, so water quality is still very important. They need to confirm if the water quality match the drinking standard or not. And a non-pump wells used for observing the elevation of the water table or the parametric surface. Okay, so commonly in that kind of well, we will not use in the pump because we just observe the water levels from the natural point of view. Wells that is used to observe the change in water levels over a period or more specifically during a pumping test. Okay, so observation wells can be used for several purposes. So this one is only for the pumping test. And some of the conditions, if we would like to use in the multiple well test, like you assess the T values. In the following talk, we are talking about the T and S values. You assess the T values using single wells is sufficient. But if you like to assess the S value, you need to use in the multiple well test, at least the 2 wells, because they need to have the distance of the 2 wells, and then you will be able to inverse the S values. Okay, so observation well is commonly used for calculating the S values, and some of that is they just drilling a very small scale size, maybe just 1 inches or 1.5 inches. That'll be easy, and then they put a parameter to the measurement, and after that wells is abundant, they just give up or just refilled. Okay. So that kind of the observation wells for the temporal usage. They are not for the permanent usage. But the original wells is put parameter for long-term observation. Okay, they do the continuous observation for that. So pump does not normally take place from observation wells, which are often relatively small in diameters. Okay, so if you have the small diameters, the pump, I don't know if you ever take a look at the pump. The pump, we put it in the water, that kind of pump is relatively larger. The small one will be relatively small, but commonly, if your depth to waters, your water level is very, very deep to the surface, you need to use a more strong pump, and then you'll be able to take the waters out. Okay. If your pump, if your power of the pump is not sufficient, it is not able to take waters out. And if you want to have the more powerful pump, you need to have relatively larger size. And they will constrain, you need to have the larger borehole, and then you will be able to put the pump inside. Okay. That's also a very important part because last 2 years, I tried to evaluate a project. I tried to give the comment for a project. They drilling the borehole in the very nearby the rivers. They want to assess we call it hypohalic waters. And they just drilling maybe just 2 inches borehole because they just imagine, oh, we just want to measure we just using observation wells. So they're using 2 inches of the borehole. And then after that, they're doing a pumping test. And then match one problem is that their water level will not have the decline. If we doing the pumping test, we using the ground level decline behaviors to estimate the T values. Okay, if the water level decline very fast, that means you have the very less T values because the water level decline largely, or you have the less S values. And if your material, like you can imagine, if the material is gravels, you pump waters. If you pump very less waters, the water level, because they can easily flow into the wells, so the water level will not have significant decline. They will very fast to supply the waters in the wells. Okay. So their problem is that they try to using the 2 inches wells and 2 inches well and put the pump inside, but they doing the maximum power, but the water level still keep constant because that's gravel. The material is gravel. I mean, I said that they are very close to the river bank, so they are mainly for the gravels. They are high permeable material. So in that area, you using a pump, you need to use a more powerful pump to decline your ground levels. If your pump is not strong enough, your water level is stable. You are not able to see the decline. And if you are not able to see the decline, you are not able to assess the T and S. Okay. So they meet these problems because their pumping test failed. They are not able to see the water level decline, and they cannot use that to assess their T and S. But their contract require you need to assess the T and S for each of the site. And another part is that you can reduce. For example, you can try to use in a larger borehole, right? You can drill in another borehole to do again. But you meet another problem is the budget. Because larger borehole means you need to spend much more money. And another is you already drilling one borehole. You spend all the money, the budget for the borehole. But you need to drilling another borehole. You need to spend another budget for that. And commonly for last time we drilling 30 meters of the borehole in the Thai coast, we spent around 300,000. Okay, $300,000. Okay, so it means you want to construct a borehole, it spend money, and if you need to drilling an extra borehole, that means you need to spend another money. Okay, and they do not have the budget, so they mention that they cannot drilling another new borehole for this work, but they are not able to gather the data. So that time I asked them how to solve these problems, and they're using the modeling. Okay, they're using another inverse method to overcome these problems. But honestly speaking, it's not a success because just to remind you that you need to be careful. For example, if you know the site have the high permeable materials like gravels or the boulders. You need to use in the larger scale borehole, and then you need to put the strong pump inside, and then you will be able to see the decline of the levels, and then you can assess the T and S value. Okay, or you will meet the problems. You need to spend much more money. Okay, and you might get fired by your boss. Okay, because you made a mistake. You need to spend much more money. You cannot earn money like that. Yeah, so some experience to share to you. Seems we might not have time, so I think maybe we can stop here first. Okay, and see if you have any questions about today's talk. To provide some of the background for the hydrogeological survey, because hydrogeological survey it can include a lot of different disciplines, and it's not easy to done all of the content, and especially commonly we are only focusing on a topic. We are not able to do all of the work, so we might also need to integrate different people or group together, like a chemical part. You might need to find a lab, they are able to analyze the chemicals, or you might need to find the companies, they are able to help you analyze the chemical compounds. And physical part, you also need to find a company to help you drilling the wells, doing the pumping test. Like Professor Ni's lab can do the pumping test, you can also hire them to do the work. And each of the components need to spend money, and you need to manage your budget wells. And after you have data, you might need to control the models. You need to have the software for your modelings. You need to understand how to do the simulations. Okay. And you also need to know how to construct the hydrogeological models first, okay, before you do the simulations. So there'll be a lot of steps. And some part you might be able to handle, but some part you are not able to handle, like well loggings, how to do the well logging geophysical survey. You might also need to find other companies to collaborate together. So how to integrate all of the information together and then got a project or got the solutions for your work. That's a very tough step. Originally, Professor Dong also want to propose one of the classes. We try to use in the project orientation concept to teaching the students how to operate a project from the beginning, like a surveys, and then doing the report. Yeah, but honestly speaking, it's not easy. It seems they take much more time to complete all the components. Yeah, so that time we do not propose this kind of courses. Yeah, but I think maybe like this course will provide some of the background how to do this kind of survey and control the hydrogeological models. And then you can use that for your purpose, civil engineering work and groundwater work, and like engineering geology work. Okay, so they can be used in different disciplines. Yeah, but I hope you can understand some of the background informations, how to do that, and what's the important things you need to take care. Okay. If no more questions, we'll stop here. Okay, thank you very much.